This video is about potential outcomes and the average treatment effect. So here, each individual is a pair of cards, one black and one red, where the black represents the treated potential outcome and the red represents the untreated potential outcome. So we can imagine, so each column is sort of a single individual, and then each row is one of two parallel universes for that individual. So if this individual is in a universe where this individual is treated, their outcome would be 3. If they're in a universe where they're not treated, their outcome would be 8. So we can see sometimes the treated potential outcome is higher. It could be 10 instead of 2, so the treatment is really helping this person a lot. The second person, the treatment actually hurts. So they would be 8, but then when they're treated, it drops down to 3, assuming higher is better here. Third individual, there's just no effect of the treatment in either direction. And the last individual has sort of smaller values and a small positive effect of the treatment. So we can also see there's a lot of heterogeneity, a lot of differences across different people. Some sort of tend to have higher values or lower values, or big treatment effect or little treatment effect, or negative, positive. So everybody is different, as we could imagine. But when everything is so different, it can be kind of difficult to communicate, and we often want some way to summarize all of these numbers. So one way to do that is with the average treatment effect. So the idea there is, bring out a paper now, so here I've just written down the treated numbers 10, 3, 5, 4. Here's 10, 3, 5, 4. And then the untreated 2, 8, 5, 3, this bottom row. Then for a given individual, like we said, their treatment effect is the difference between the treated and untreated potential outcomes. So it's sort of, if we keep the universe exactly the same, except we treat you instead of not treating you, how much different is your outcome? So first individual, 10 minus 2 is 8. We already sort of talked through this. Second individual, 3 minus 8 is minus 5. 5 minus 5 is 0. 4 minus 3 is 1. So these are all the individual treatment effects down here. And obviously we might have more than 4 types of individuals in the population, so there could be a lot of different individual treatment effects. There could be an infinite number, potentially. But let's imagine even if there are only 4 types of individuals in the population, maybe each type has 1/4 probability. Then instead of reporting these 4 numbers, we could choose to report the average treatment effect. And so in that case, if the probability is 1/4 for each type, then the ATE is the average, that's the expected value, average treatment effect. So that'll be probability times first value is 8, just the usual expected probability formula, where each probability we've assumed is 1/4 just for simplicity. So that'll zero out. And then we'll have 8 minus 5 is 3, plus 1 is 4. Just factoring out the 1/4 here. 1/4 So again, that's 4, 4. So that'll just be 1. So the average treatment effect here is equal to 1. Again, that does lose a fair bit of information about the heterogeneity in the population. It's not that everybody's treatment effect was equal to 1. One person's was. One person's was much greater than 1. One person's was actually negative. So if we just look at the average, we lose some information, but the benefit is we just get one number that's more simple to communicate. So as always, there's a trade-off.